Okay, this is number 29, again in section 2.3. And the directions say find, so the general solution of, okay, so equations 27 through 32, so we're in 29. So we're obviously finding the general solution. We've been doing that. But it says first find a small integral root of the characteristic equation by inspection, and then factor by division. So they're talking about synthetic division or long division. The small integral root, integral in this case meaning integers. So we want an integer root, which is nice. It could be a rational root, but it's going to be a nice integer. Okay, so let's start. So using the characteristic equation, right? There's an associated equation, a polynomial equation. So we have r cubed plus 27 equals 0, right? Remember here, r is equal to the first derivative. Okay, so here, again, can we factor this polynomial? Well, there's definitely no GCF, right? I mean, there's 3 r's here, there's no r's here. Can't use a quadratic formula because it's not quadratic, right? The highest power is 3, right? It has to be a 2 in order to use a quadratic formula. So this is actually a special polynomial that you've seen in algebra many times. So I'm going to go ahead and just, well, you're going to see it again. But this is really, okay, we can, obviously this is r cubed. But notice 27 is a perfect cubed, right? I can rewrite that as 3 cubed. So there's a formula, right? There's a sum of cubes and difference of cubes. So a b cubed plus a cubed plus b cubed is a plus b. That's one factor. And then the other factor, right? One way I like to, I remember it is I know a squared, and then I know b squared, and then it's just times the product of a and b. So ab plus that. So this factors to these, right? These are two factors, right? Maybe let's write, this is going to be your integral root that you're going to find, right, in this part. And then this guy, let me maybe write it in green. This is where you probably use the quadratic formula, right? This actual expression is not factorable over the real numbers, so you are going to get a complex root. So might as well go ahead and write that out. When you have a sum of two cubes, you'll get that complex root. Okay, so let's go ahead and factor this guy. Well, we have, so I'm here. So we have r cubed, right, plus, and again, we can rewrite this as 3 cubed, that's fine. So how do I factor this? Well, I'm just following the formula. So a plus b, well, my r is my a, right, and 3 is my b, right, a, b. So that's going to be r plus 3. And then the next one's going to be, let's see, a squared, so that's r squared. Okay, my b squared is 3 squared. And times ab, well, a times b. And this stays the same. And then this is r squared plus, and then, right, that's just 3r. That's a plus sign, plus 9. Okay, so I just factored, right, this polynomial, and this is a very popular and very nice polynomial because we know, well, if we set that equal to 0, right, what's the root? Well, we know one of the roots is going to be -3, right? There's your integral, right? It has nothing to do with integration. They're talking about integral implying, again, integers. Integral root. Okay, so check, that's done. But again, what about this guy, right? Whoops, should be green. What about this guy, which is still blue again? Okay, so let's factor this guy. Let's use a quadratic equation. So I'm going to use, right, quad formula on this guy. So we have r equals negative b, so negative 3 plus or minus the square root of b squared, so that's 9 minus 4ac, and that's a 9, and then all over 2a, which is just 2. And again, just simplifying, so negative 3 plus or minus the square root of 9 minus 36 all over 2, and plus or minus, right, 36, 26, 25, 27, actually 27 over 2. Okay, so again, it's going to be a complex root because of that negative, and I think I used maybe this shade of green, right? So definitely going to be a complex root. And I mean, this is always the case. You are going to get a complex root when you have the sum again, or difference of two squares, or two cubes. So this is some fun algebra. Okay, we know there's going to be an I out there. We can, well, okay, we know there's going to be an I, so I'll just go ahead and put the I there. So we're just really evaluating. So if you want to do work on the side, that's okay as well. You can do, okay, so the square root of 27 is the same thing as 3 times 9, right? Whoops. And then 9 is a perfect square, right? So that's really the square root of 3 times 3, or we can say 3 root 3. So this is really 3i times root 3, or you can actually say 3i root 3, and then I'm going to divide by 2, and we can just break it up here. Okay, so what do I get? I get r is equal to negative 3 halves, right, plus or minus 3 halves, and I wrote the I here, okay? It actually doesn't matter where I write the I. I can write it in front of the radical, or I can write it after the radical, okay? Just make sure not, don't do, or don't write, this is wrong, if you write the I under the radical, okay? It has to be the square root of 3 and then times I, so this is bad, so don't do this part. Okay, so the reason I put the I at the very end is because now we can easily see that this is your A, and then this guy is your B, right? There's your complex number. And so these are your complex conjugates, right? And let's go ahead and write, actually the first, let's go ahead and denote the first, our first guy was negative 3, right? Our integral root right here. So I'm going to go ahead and call this, oops, R1, right? Because that was my first root. And then now I'm going to call this one of them, R2, is negative 3 halves plus or minus 3 halves root 3 I, and just kidding, not one is plus and one is minus, so negative 3 halves minus 3 halves root 3 I. Okay, so here are our complex conjugates. Okay, and we're almost done. It's Friday night. It's been a long day, but okay, let's keep going. We're almost there. Okay, so the first one, again, I'm gonna go ahead and write I'll write R1 right here, and it was, I believe, negative 3. So here, okay, here are all my roots, okay, and again, complex, right, and this is not repeated, right, this is just a regular, I mean, I want to say this is a real root. I really shouldn't say distinct because, well, these are, I mean, compared this one and this one, I mean, they are distinct, but here it's a nice real root, integer root. Okay, so now how do we write our general solution? Well, this guy, again, from the theorems we've been using, right, the two, let's see, just to refer here. So theorem 1, right, our conclusion, right, this is our distinct roots. So C1 e to the R1x, and it's going to bug me, y equals, okay, C1 e to the R1x, okay, to the negative 3x. Okay, that part is done, right? That's this guy, so check. Plus, and these are complex conjugates, so my complex conjugate pairs, right? I'm going to be using theorem 3, my complex root. So again, I'm going to write, well, let's go ahead and write it. E to the ax. Okay, what is my a? Well, my a, right, from above is just negative 3/2, right? Here's my a, and then here's my b. And so ax, so that's negative 3/2 x, and then, okay, times C1 cosine bx. Okay, what's my b? And I'm just going to write this in parentheses. So bx, let me, oops, make this, shrink this a little bit. Okay, so plus C2 sine bx. So there's my b and x. Okay, so complex, right, from the complex root, and this just from my nice integer root. And let's see, what did it, I think they said they wanted the general solution, so I want to say we are done. And yep, they wanted the general, yeah, find general solutions. So that's it. This is our final answer. Wow, that was 12 minutes and 35 seconds. Good job. Way to hang in there.